Hello, welcome to another video of Dr. Vivs. Even though these are graduate level videos, we would sometimes like to solve interesting and fun problems because the best way to understand theory, in my opinion, is to solve difficult problems and see how the theory works. So specifically in this case, we'll be using Lagrangian dynamics to solve a problem. Now, the undergraduate version of this is usually the wedge is fixed and there's a ball rolling down the rough surface and you're asked to find, for example, what the speed of the ball would be at the end. In this problem, the wedge is not fixed. It's free to move, but the ball is still on the rough surface, so there's no slipping in this problem. Now, the way I've specified the object is using the radius of gyration. So I have to define what that is in case you're not familiar with it. Engineers like to use the radius of gyration, and they define it as that radius k for which the object looks just like a ring. So you can have a very complicated object rotating about its center of mass, but you can define a very simple quantity called the radius of gyration, which will make it look like just like the ring. So k here is called the radius of gyration. Engineers have listed the radius of gyration for different objects. Typically, it's going to be some fraction of the actual radius of the object. So in this case, k will be some fraction of r. At the end, we'll specialize to a specific example. At the end, I'll take m to be capital M, h to be 1 meter, g to be 10 meters per second squared, alpha to be 30 degrees, and the object that's rolling to be a solid sphere. So in this manner, we can really see what the radius of gyration is for this problem. So what we are asked to find is how long it stays on the wedge and how far the wedge has moved. Obvious things to find in this problem. Now, when we are doing a problem with Lagrangian dynamics, the first thing you have to do is draw a really super clear picture. So let's do that. The ball will be starting on the top like that and ending over here. At some intermediate point, the ball would be over there. I'll draw that with solid line. Now this coordinate, which goes from the center of mass of the ball and keeps track of the center of mass at any time, I will call the coordinate x. So x will be a function of time. When the object has reached the full distance, the x will be x of tf, which I'll simply call xf. Okay, so that's the length of the entire incline is x of tf. The other variable I'd like to define is the height. Now height, even though the problem statement says the height is from the center of mass at the beginning to the center of mass at the end, I'd like to simplify the treatment, and so I'll interpret the height as follows. I'll interpret the height as the actual height of the wedge, because in other words, I'm keeping track of the point of tangency of the ball to the point of tangency, and that's the same height as center of mass to center of mass. So it's not really an assumption as much as common sense. So this is your angle alpha. Let us immediately find a relationship between h, xf, and alpha. By trigonometry, opposite over hypotenuse is the sine of the angle. So that tells me that xf is h cosecant alpha. So we have that nice relationship. The other thing I would like to do is see where the height of the ball is at the point of tangency. So I'll call that a little h, because the potential energy is going to be measured with respect to little h. So again, the potential energy is 0 will have to be defined, and that's defined as the bottom of the incline. So the top of the incline, the potential energy of the ball is going to be mg little m times g times capital H. So we're not worried about the center of mass anymore because of this simplification I told you about. or rather the shift of viewpoint. Everything is shifted down by a radius r. So that's what we have. The radius of the ball is little r. The mass of the ball is m. The radius of gyration is k. The mass of the wedge is capital M. Now we have to find a coordinate system for the wedge. That's very simple. The wedge is not moving up or down. It's just moving to the left. So let's call that coordinate system of the wedge capital X. I'm going to try to make my capital X and little x to be sufficiently different looking, so you won't get confused. Well, one more variable is importantly missing, and that is the rotation. That's going to rotate. So let's call that angle phi, the angle with which it rotates. Okay, so now we have defined all the variables, and we can proceed to start solving this problem by the Lagrangian method. So the first thing we have to do is understand that when this ball starts rolling, the wedge is moving to the left. So you have to use the concept of relative velocity. In other words, the center of mass is not just given by x dot. It's more complicated. So the velocity of the center of mass has got two components. It's got the x component and the y component. Well, the x component is going to be the x cosine alpha, but it's also going to have something subtracted from it. It would have been x cosine alpha if this were not moving, but because it's moving to the left, you have to subtract this amount from it. So the relative velocity is going to be x dot cosine alpha minus capital X dot squared. And the y component is just x dot sine alpha squared. So that's our VCM squared. Let's simplify this. If I simplify this, I get x dot squared cosine squared alpha minus 2x dot cosine alpha plus x dot squared. And then I get x dot squared sine squared alpha. Now sine squared plus cosine squared is equal to 1. So we can just use that. So I get x dot squared minus 2x dot cosine alpha plus x dot squared. And this is the exact result you would have got by using the triangle rule, also known as the cosine rule. So the first equation we have, this equation is actually a constraint. It's a constraint for remaining on the wedge. If the velocities do not satisfy these constraints, the ball will start flying from the wedge. So that's the first thing. What about the next constraint? We also know the ball does not slip. So the no slip condition will have to be incorporated next. So let's do that. So we'll call that the no slip constraint, or the no rolling without slipping constraint. Well, that tells us that the linear velocity is related to the angular velocity through the no slip condition. So VCM is going to be r times phi dot. Now, I want to just pause because in addition to showing the right way to do some problems, I also want to talk about the common pitfalls. What would be a common blunder in this problem? So a common blunder. Let's say someone is in a hurry and they're not thinking very clearly. What they will do is this. They'll write x equals r phi. It seems pretty convincing that if you travel a certain distance, then the relationship between x and phi is going to be x equals r phi. And then they'll differentiate to write x dot equals r phi dot. That's completely wrong. As you can see, x dot is not equal to r phi dot. If I square this equation, I'll get x dot squared equals r squared phi dot squared. But if I square that equation, I'm going to get VCM squared equals R squared phi dot squared, and VCM squared is this awful looking thing. So this is the wrong equation because it does not take into account the movement of the wedge. Now, because the wedge moves, the ball is actually going to roll faster and faster because it's you can think of the wedge moving as making the wedge steep. So the true path of the ball will be something like this because the wedge is moving. So actually the ball is going to move faster and faster because of that. That is not reflected here. It is reflected here because of the negative sign. Okay. So this entire thing will now give you the correct answer. That's the common blunder you have in this problem. Now, once we have avoided the common blunder, let us now write the Lagrangian and incorporate the constraints straight away. Incorporating the constraints mean that we are sacrificing full knowledge of the constraint forces, which in this case are the normal force. Normal force tells you that the ball is being felt by the wedge. In other words, this constraint gives you the normal force, and that constraint tells you the ball is not slipping. In other words, that constraint gives you the static friction force. The normal force and the static friction force are now mystery objects because we are incorporating the constraints. But I'll just write here the constraint force associated with each constraint. If you actually need to find the normal force and the static friction force, you'll have to enforce the Lagrange multipliers, and it takes us a little bit towards the 1.5 hour video territory rather than a video that lasts about 40 minutes. Okay, I want to keep this reasonable length. So let's write, of course, the motivated student should try that on their own using Lagrange multipliers. So let's try the kinetic energy term. The kinetic energy term is going to be the kinetic energy of the wedge plus the kinetic energy of the translational kinetic energy of the ball. I'll call it a ball instead of a rolling object, plus the rotational kinetic energy of the ball. Now, let's incorporate the second constraint immediately. So I get 1/2 m x dot squared plus 1/2 m VCM squared plus 1/2. Now for ICM, I'm going to write mk squared because that's the radius of gyration. And for phi dot squared, I'm going to write VCM squared over r squared. Now this k squared over r squared is going to keep coming if we do not do something about it. So let's quickly define a parameter, eta, which is going to be k over r. I'm going to follow the notation of putting a colon to the left of the equal sign, which means that the quantity to the left of the colon is being defined by the quantity to the right of it. That's a common notation in advanced mathematics. So I'll start using that henceforth. So we'll write everything in terms of eta. Now observe that you have 1/2 mv squared here and 1/2 mv squared. So you can take that eta squared, which is k squared over r squared, together with that and write a simplified kinetic energy term. So the simplified kinetic energy term is 1/2 m x dot squared plus 1/2 m 1 plus eta squared times VCM squared. So maybe later on I'll do something about m times 1 plus eta squared, but right now it's looking reasonable. I mean, I wonder if I should do it right now. So let me define another quantity. Let me define another quantity just to make things even simpler. I'm going to call m tilde equal to m times 1 plus eta squared. So this definition will make our Lagrangian look really simple. So I've incorporated the rolling motion of the ball into some new kind of mass, like the effective mass. You can think of it as an effective mass of just a sliding object. So we have converted the rolling object into a sliding object, in other words. Beautiful. So I've converted what looks like a very difficult problem to what looks like a slightly less difficult problem. You just have now got a wedge that's a block sliding on a wedge, and the wedge is moving to the left and the block is moving down. So no longer you have to worry about rolling. So I'll see what I've, the accomplishment in this page has been converted the problem to a block of effective mass m tilde on a wedge. Now all we have to do is write the potential energy term and then the Lagrangian. So let's proceed to do that. The potential energy term, remember the zero of the potential energy is here. At any given time, the potential energy term will have two terms. One, the potential energy of the wedge itself, and the second is the potential energy of the rolling object. The rolling object at an intermediate point is at some height, little h. So let's write the potential energy. U is, now by the theorem of geometry, G sub E is Earth's gravity. So by the theorem of geometry known as Apollonius's theorem, the center of gravity of a triangular wedge is located at the 1/3 height. Okay, that's a standard result in elementary geometry. So that's h over 3 plus mg times h, because we have agreed that the potential energy of this object is going to be reckoned from the point of tangency. Now all we have to do is write our little h. Well, little h is capital H minus this distance. And this distance is just x sine alpha, right? Because this angle is also alpha. So we can write little h in terms of capital H and x as follows. I'll stop writing the G sub E. Well, that looks really good because there's a bunch of constant terms, and I'm going to call those constant terms U naught minus mgx sine alpha. I'm going to underline all the terms I've called U naught. U naught is this and this. Okay, I'm underlining those. That's what makes up U naught. Ultimately, when we differentiate the Lagrangian, the constant terms will not matter, and so these constant terms are going to simply get in our way, and that's why I got rid of them. Now we're ready to write our Lagrangian. Lagrangian L is T minus V. T minus U in this case. So the kinetic energy term is that it's 1/2 m x dot squared plus 1/2 m tilde. Now VCM squared was here. So I'm going to copy that. Little x dot squared minus 2x dot capital X dot cosine alpha plus capital X dot squared minus the potential energy term. So that's going to be, this is all going to become a minus. So that's minus U naught plus mgx sine alpha. There's our beautiful Lagrangian. The Lagrangian is a function of x dot, capital X dot, and not of time. So right there, you notice that because it's not a function of time, there's some energy conservation that's possible if we go to the Hamiltonian viewpoint. We're not going to go to the Hamiltonian viewpoint, but I'm just mentioning this to you. The other thing you'll notice is it truly does not depend on x. So we can expect linear momentum conservation. Along the direction x hat. And we will see when we do the equations of Lagrange that indeed linear momentum is conserved. But just by looking at the structure of the Lagrangian, we already expect energy to be conserved. We already expect linear momentum also to be conserved. So that's something you know from elementary classes. If you have a block going on a wedge and the wedge is moving, then of all the things that remain conserved, you will have two things. One is energy and one is linear momentum. Okay, so now we'll do the x equation, little x equation. The great Lagrange Lagrange used D'Alembert's statics equals dynamics principle to derive this, and later Euler came and derived it using the variational principles. And so these are collectively called the Euler-Lagrange D'Alembert equations sometimes. So the x equation is d by dt of del L over del x dot minus del L over del x equal to 0. So now it's just a matter of looking at the Lagrangian and doing the math. So d by dt, when I differentiate with respect to x dot, I pick up a contribution from here and from there. So I'm going to get m tilde x dot. That x dot squared will produce a 2x dot when differentiated, and that 2 will take care of the half. Here, when I differentiate with respect to x dot, I still have a 2 here, which will take care of the half. So I'll lose a 2 in both cases. So little x dot minus capital X dot cosine alpha is what I get. And then minus del L by del X. That just gives me mg sine alpha equal to 0. So I can expand this out a little bit. I'll take a double derivative. Since m is not changing, I'll write m tilde x double dot minus m tilde x capital X double dot cosine alpha minus mg sine alpha equal to 0. This I will call my equation 1 and return to it later. I can't do much with it because it's got little x and capital X, and I don't really know what the relationship is between the two. Hopefully, the next equation, capital X equation, will actually give me a concrete relationship between the two. Let's find out. So the capital X equation can be got by the same procedure, except you replace little x by capital X. Here's where my observation earlier comes of use. This is 0. Coordinates where del L by del X is 0 are known as cyclic coordinates. If you have a cyclic coordinate, then a theorem of Noether says that the corresponding momentum is conserved. Why is Noether's theorem true? It's true because of this. If d by dt of something is equal to 0, then it means that whatever that is must be constant. And that quantity that's inside there is called the canonical momentum. So the canonical or the canonically conjugate momentum to x, written pi x rather than px, which is del L over del capital X dot, is conserved. In other words, it's equal to a constant. So we're going to work with that equation. Del L over del capital X dot equals constant. Well, the Lagrangian is there. Let us now solve this equation, and the constant can be then determined using the initial conditions. When I differentiate with respect to x dot, I'm going to get from the first term capital Mx dot. And then from here, I have two contributions, one from here and one from there. When I differentiate here, that 2 will cancel with that half. When I differentiate here, I'm going to get 2 times capital X dot, and that 2 will cancel with a half again. So once again, I lose the 2's. So I get plus M tilde. I'll write this term first. Capital X dot minus, and then this term. X dot cosine alpha must be equal to a constant. So I have capital M plus M tilde X dot, and then minus M tilde little x dot cosine alpha equals constant. Now it's time to get rid of the constant. So we're going to use the initial conditions to do that. The initial conditions tell us that when the time was 0, neither the wedge nor the ball were moving, which means the constant must be equal to 0. Because this, I can say to myself, I'm going to consider this equation at time 0. And by putting 0 there and 0 there, I realize that the constant must always be 0. So that fixes our constant. Therefore, we have x. What I can do now is I can differentiate both sides. So you really don't need to fix the constant because I'll be differentiating both sides, but it's good to know that you have this relationship. Let me write the relationship first. I have x dot is equal to M tilde over M plus M tilde times little x dot cosine alpha. So this establishes a relationship between capital X dot and little x dot. So the velocities are related like that. And now we differentiate with respect to time again. So I get x double dot equals M tilde divided by M plus M tilde, little x double dot cosine alpha. I'm going to box this because it's a important piece of information. It connects the two velocities and the two accelerations. So I'm going to call this my equation 2. What we are going to do next is use equation 1 and equation 2 together and finish solving the problem. Let us put equation 2 in equation 1. I'll keep them right above each other so you can see the action. Well, equation 1 has got x double dot there. So I'm going to write M tilde over M plus M tilde, little x double dot cosine alpha, but there's another cosine alpha there. That gives me cosine squared alpha. So now I have an equation purely in x double dot, which is really great. So we can solve for x double dot. Now, I can take out mx double dot common from both terms, and let's see what I get. Then I'm going to get 1 minus m tilde over m plus m tilde cosine squared alpha equals mg sine alpha. Let's pause for a moment to see if all this makes sense. We have done a lot of work and everything's looking strange, so it might make sense to consider the limit of the wedge being, let's say, zero mass. Okay, if the wedge is very light, you expect the x double dot, the object to simply fall straight down. Okay, because if the wedge is really light, it scoots out and the ball is just left. It's like one of those cartoons. You don't have anything, and the ball realizes, oops, there's nothing under me, and it just falls straight away. Well, let's see if that is true. If m is 0, then I'm going to get m tilde x double dot, and then I have 1 minus m tilde over 0 plus m tilde, so that cancels out. Cosine squared theta, cosine squared alpha equals mg sine alpha. So I have, even in this limit, there are surprises. So I'm going to get m tilde x double dot sine squared alpha equals mg sine alpha. One of the sine alpha factors cancels out, and so I'm going to get x double dot equals m over m tilde. Now, remembering what m tilde is, it is m times 1 plus eta squared times g. M cancels out, so that's, and then there's also a 1 over sine alpha. So that is g over 1 plus eta squared sine alpha. Now, if eta is 0, that's g over sine alpha. That'd be a block. Now, acceleration is not quite g, it's g over sine alpha. Well, I don't know if that makes sense to you. I'm not immediately able to see it, but the constraint of the wedge immediately moving out leaves you with an acceleration which is g over sine alpha. But anyway, I'll leave that as it is. And now let's proceed to work out the problem. Now, this quantity is all constant. There is no reason for me to keep carrying it around. So what I'll do is I'll call this yet another definition. So this is par for the course in higher level work. You keep defining new things. So I'm going to define this to be zeta. Okay. So now I can write mx double dot zeta equals mg sine alpha. And that tells me what x double dot is. X double dot, oops, that's m tilde. It's m over m tilde times g sine alpha over zeta. So that's an important moment. We realize the right-hand side, even though it looks complicated, and we will soon write it in its full glory, is actually a constant, a complicated constant. So we can integrate it. So we integrate to get x dot equals m over m tilde g sine alpha over zeta times t plus some initial condition, which is x dot at time 0. Well, that we know the velocity of the ball at time 0 is 0. So that center of mass velocity is 0. So that's taken care of. We integrate it again. That gives me x as a function of time. The integral of t is t squared over 2. So that's 1/2 m over m tilde of g over zeta sine alpha t squared plus x at time 0. Well, we know that when the thing was initially at the top, that x line that extends from the top to where it is also 0 length. So that's going to be 0 also. So the last thing we have to do is fix the time. One of the aims of this problem is to see how long the rolling object is on the incline. So we're answering the first part right now. Now, to do that, we have to use the fact that when the object has come to the end, it has covered a distance x sub f. But x sub f is h cosine alpha. So let's use that piece of information. So this is part 1. At time t equals tf, x of tf is x sub f, and x sub f is h cosecant alpha. So now all we have to do is use the fact that x sub f is that into this equation here. So I'm going to get h cosecant alpha is equal to 1/2 m over m tilde g over zeta sine alpha times tf squared. Now I have my tf. I can solve for it by taking the square root after moving everything to one side. Let me do that. So tf is going to be 2h over g. I always like to keep that combo together because that's the time taken for an object to fall down a height h in a constant gravitational field. Times, this ratio gets inverted when you take it to the other side. So I get m tilde over m times the zeta factor. And then I have sine alpha, when it goes to the other side, becomes 1 over sine alpha. But 1 over sine alpha is the same as cosecant alpha. So that combines with this cosecant to give me cosecant squared. So let me write now the time in its full glory. Tf is going to be the square root of 2h over g. Now m tilde, trying to find where I defined it. It's here. M tilde is m times 1 plus eta squared. So m tilde divided by m is simply going to be 1 plus eta squared. And eta is k over r. So I get 1 plus k squared over r squared times zeta. Now that puppy appeared here. So I'm going to get, for that one, 1 minus, again, m times 1 plus eta squared, and eta is that k squared over r squared, and then divided by m plus the same thing. Times cosine squared alpha, close flower bracket, times, when I take the cosecant squared out alpha outside, it just becomes cosecant alpha. So I have solved for the time. This nice monster expression is the time taken for the rolling object to leave the wedge. Part 2 asks us how far left has the wedge moved. So that part is pretty easy to do next. So let's do that part. Wedge has moved by a distance x evaluated at tf. But capital X is related to little x. That relationship is right here. What we have to do is integrate If I integrate, I get this. If I integrate this, what am I going to get? I'm going to get x of t is equal to m tilde over m plus m tilde x dot, x of little x of t cosine alpha plus some constant. Now to find the constant, we can use the initial condition. At t equal to 0, we had our drawing showed that the wedge's left corner was at the origin. And the left corner of the wedge is what determines the value of the x coordinate, capital X. So we're going to say x equals 0 at t equals 0. But at t equals 0, little x is also 0 because little x, mind you, tells you how long this brown arrow is. The brown arrow, when the ball was there, was no length at all. So this all tells me that the constant is 0. Now all we have to do is substitute, and I get x as a function of tf. X of tf is going to be m tilde over m plus m tilde, little x of tf, because this here is little x as a function of time also, times cosine alpha. So I've solved the problem. Now let us put everything back in its glorious variables to find out the answer. It's always good to give answers in the variables that were defined in the problem and not stuff that you made up on your own. So x of tf is equal to, I get m times, that's 1 plus eta squared, and eta is k over r, so that's 1 plus k squared over r squared divided by m plus m times 1 plus k squared over r squared times cosine alpha. Now x of tf is precisely that, h cosecant alpha. Well, the simplifier in me cannot resist writing one more step. So let me just write one more step. I'll call this xf, because cosecant is 1 over sine, and cosine divided by cosecant is cot. So this is just h cot alpha times some weird mass ratio. That mass ratio is 1 plus k squared over r squared divided by m plus m times the same thing. Another box-worthy equation, I'm sure you'll agree. In this way, we have solved a beautiful problem using Lagrangian dynamics. So all we have now got to do is to evaluate. The evaluation is for a special case of little m being equal to capital M, h equal to 1 meter, g equals 10, solid sphere, and alpha equals 30. My favorite value for acceleration due to gravity is 10, because then you don't have to worry about calculators and things like that. So let us proceed to do that. So first of all, let me write down, figure out what k is. So for a sphere, I remember that the moment of inertia of a sphere is 2/5 mr squared. Now, I don't want to make this video unnecessarily long and try to derive it, although I could. So I'm going to just ask you to look it up. Okay, now that is equal to mk squared. And so that tells me that k squared equals 2/5 r squared, which means that this quantity that I keep writing, 1 plus k squared over r squared, k squared over r squared is 2/5. So 1 plus k squared over r squared is just 7/5. So that is really nice. Now, 2h over g, let's find out what that is. 2h over g is 2 times 1 meter, and that is 10 meters per second squared. The units are all going to work out. So that's going to be 1/5 seconds squared. When you take the square root, you get seconds. So that's the units working out there. Now let us substitute everything in there. Now I've also told you capital M equals little m. Makes our life just a tad simpler. So TF is going to be the square root 2h over g is 1/5 second squared. This thing here, 1 plus k squared over r squared is 7/5. And that is 1 minus 7/5 over 1, because this little m and capital M cancel out, I get 1 plus 7/5, which is 12/5. Now, I'll write here what sine and cosine, all the trigonometry I'll do with red. Sine 30 is half. Cosine 30 is root 3 over 2. Therefore, cosine squared 30 is 3/4. That makes sense because sine squared 30 is quarters and sine squared plus cosine squared is 1. So that looks good. So cosine squared alpha is cosine squared 30. So that's going to be 3/4. That was shorter than I reckoned it would be. So let me remove the rest of the square root. All that times cosecant alpha. Cosecant alpha is just 1 over sine alpha. So that's times 2. Now that can be evaluated. So seconds I can pull out. I'm going to get square root of 7 over 5 times 5. I don't want to write it as 25 in case there's a cancellation. Let's see if there is. So this gives me 3 goes 4 times. So that's going to be 1 minus 7/16. 1 minus 7/16 is 16 minus 7 over 16. And 16 minus 7 is 9. Times 2. So it's a good thing. It doesn't really matter because 5 times 5 will come out of the square root, 9 will come out of the square root, and 16 will come out of the square root. So I'm going to get 3 over 4 times 5, which is 20. When I take it out of the square root, I'm going to get 3 over 20. And 3 over 20, with the numerator, I have 2. So I'm going to get 3 over 10. So the answer is going to be 3 root 7 over 10 seconds. This is not terribly important, but that's the time. Now, how far has it moved? Well, it's moved a distance that's equal to that. So that's the next thing we have to evaluate numerically. Let's do that also to finish up the problem. XF is capital H, which is 1 meter. Cot is cosine divided by sine. So it's just root 3. Now here I have a m and capital M being equal. So that cancels out. It's just the same as that actually. So I'm going to get 7/5 divided by 1 plus 7/5, which is 12/5. Cancel out the 5s. I don't think this can be simplified anymore. So that's going to be 7√3 over 12 meters. That's how far the wedge itself has gone to the left. Let us, I just want to make sure this thing makes sense to me. I always like to check these kind of things. That's 1 meter. This is 30 degrees. So if it comes down, let me just try this this distance. This distance is going to be, if I call this distance y, then 1 over y is going to be tan 30 degrees. And so y is going to be cot 30 degrees. And cot 30 degrees is going to be √3. Now, our problem would be a complete flop if this distance moved was bigger than √3. Well, thank heavens it's not. So xf is less than √3. In fact, it's 7/12, which is less than 1. So this passes the common sense requirement in this problem.